Good afternoon. See, in the morning class, we just have started with important fundamental equation called impulse and momentum equation to account non-central impact problem, to solve non-central impact problem. So we have not gone into exactly the equation of non-central impact problem. Rather, we were just trying to understand the other form of Newton and Euler equation, which can be represented as principle of impulse and momentum equation. So wherein then we have understood, like we have seen for a direct central impact or oblique central impact, application of linear impulse and momentum equation, you would see that similarly angular impulse and momentum equation is also essential when you have to solve problem of non-central impact. So that's what in short that we have seen in the morning lecture. I'm going to derive now the expression required or the equation required to solve the problem of non-central impact problem. So what is that expectation out of this collision problem? Is that when the two bodies or the two vehicles, when they collide, the center of gravity of the colliding vehicle is not going to be along the line of impact. So they would be at different locations, and the contact normal, whatever that you draw of the two vehicles, represent the line of impact, where centroid of both vehicle will not necessarily to fall on that line. So in such cases, the impulsive motion occurred due to exchange of huge magnitude force in short duration is what is called non-central impact. That's the definition of non-central impact event. So now let us look at how are we going to have the equations to solve after the collision to find out the velocities of the colliding vehicle. So if you have that, then it's easy for you to estimate what is the energy loss during the collision. So the energy loss is what is the energy absorbed, you can see, and hence you know what would be the rebound energy and so on. So this is what is the idea of learning this particular part of module 3. So let me share my active inspire board. So we exactly in the morning we have seen what is the application of impulse and momentum equation for plane motion or general plane motion of a rigid body. There you see system momenta plus system impulse, external impulse is what is going to be system momenta at another time T2. Then we also looked at this non-centroidal rotation. So any general plane motion can be expressed as non-centroidal rotation, wherein it would have an equation which is only angular impulse and momentum equation written here by Roman letter 1, which would be quite useful for solving non-central impact problem. So this is what we have seen in the morning class. So in this lecture now, let's continue to understand its application in detail for this eccentric impact. So this is lecture number 15. Today it is 28/07/2021. Let's look at what is this eccentric impact. Eccentric impact, or it is called non-central impact. So impact of vehicles that you can see. So as usual, let us consider two colliding vehicles given arbitrarily by this type of rigid body. So I have one rigid body represented like this, and I have another rigid body represented like this. These two rigid bodies are in contact at this point, and I draw a contact normal. This contact normal NN is what is your line of impact. And the centroid location of these bodies are at different points. So now here the velocities of these colliding particle at this point A on this body side, and the other body side is B. So this is B and this is A. I have velocity vector of this linear velocity at this point A for this body as VA, and for this body it is VB. Okay, VB. So if I have its component along this, that component will be here along this line. So this is how the two rigid bodies velocities are represented in general. This is VB. This is just before collision. So let us call this figure as just at the beginning of collision, right? Just at the first contact during collision is what is this A? Just at the beginning. Just at the beginning of back. And then you see, then the crash event is going to have two phases. One is deformation period. So during deformation period, you see there would be a common velocity. So that to understand, again, let us look at this body A. It's identical. I am trying to draw. Please understand that. And since it is maximum deformation, there will be smaller deformation here. And you see that again, this line of action is same as that of the same line of impact. So now here the velocities would be what? The velocities would be such that I would have, there would be reduction in this magnitude and increase in this magnitude. Maybe it is something like this. It is now UA, because it is the common velocity UA, and the velocity of this contact point here, maybe say this is UB. And if you look at it, is the length of this along the line of impact is same. So the component, whatever that I'm going to have along this is one component, and this is its component. This angular orientation is such that the component along the line of impact is going to be same magnitude, whereas the other component, vertical component, not necessarily so. Vertical component means it is along the tangent plane of impact. That is not necessarily same, but you see the length of this vector, which is along NN, is what is of same magnitude, right? And this is what is at the end of deformation period. So this figure is at the end of deformation period. So what is the next event? Restitution period. So end of the restitution period is just about separation. We are going to separate it. So if you look at that time, the orientation of this body, they're just separated. So I just draw very closely, but not in contact. So this. So now you have this side and this side, two velocities, and the velocities are just after impact, the velocities. So let's call that velocity is VA dash, and the other velocity is VB dash. And of course, you have this line of impact because it's just the instant when they are separating. Same, this is their line of impact axis. So you would have this velocity increase in magnitude compared to that of this. So this is what is your three scenarios. So what is this? It is just to separation or end of, at the end of restitution period. The end of restitution period, you would see this. So now, as we have looked at and defined, the coefficient of restitution is given by E by restitution impulse R dt with that of P dt. Right? That's what we had given. We have defined it. And you have to prove that. And with this definition, you have to prove that now VB dash along N minus VA dash along N is what is this is after collision, what is the velocity of that contact point, and would be equal to E times velocity, relative velocity before impact. That's going to be VA minus VB along N. So I have to prove now this equation. So let's call this equation as 1, this equation as 2. So I have to prove now equation 2 in our case. So how do you do that? For that, let us apply now an impulse and momentum principle. So for that, what I will do? So now let us look at what is the momentum of this. So let me take one body now, one vehicle, and draw. So what is that one vehicle? Let me take vehicle with the contact point A. So this point A. So here I had this is the N line of impact, and then the centroid of this is located somewhere here for this body, and you have now its initial momentum as it is by VA. Initial velocity at point A, and that is now being shifted here. So you see that will be represented like this. So M A B A N. One along this, another one is perpendicular to this line of impact. That is M A B A T. B A T. And along with that, you also have now a couple. That couple would be I bar to omega, I bar into omega. So you understand there is the velocity here. So mass times velocity over here is what is now taken over here, and it is being represented by this. So the non-centroidal rotation, instead of that, see, there is no constraint in this body, in this vehicle. So I take the point of reference as my center of gravity of the vehicle itself. If that is so, you would have now the momentum present in this is because it is general plane motion. So we assume it is 2D motion, and the rigid body would be having its general plane motion with reference to the reference plane, which is symmetry plane of the body. So if that is so, you would have at CG now its linear momentum as well as angular momentum are represented like this. So this is corresponding to body A or vehicle A just at the beginning of the impact. At that time, what would be the force that is acting on it? The impulse that is acting on this body, would be, so let's call this is line of impact, and I have CG over here, G. So I will have now, this is located where it is located at a distance R. It is located at a distance R, and there is an impulse that is acting. That impulse is what is called deformation impulse. So that is offered by B onto A. So this is point A, and this is offered by B onto A. That's called PDT. PDT. So what is this? This is at T1, and this is going to be an external impulse 1 to 2. This plus is what is going to be at T2. I have to get at T2 you would have, so this plus is what is equivalent to is equal to same. I have to draw the same body. Let's understand whatever that I draw. A is of identical shape because it's rigid body problem. So this is all this A, and this now at the time of maximum deformation, that is the end of deformation phase, I would have here the velocities with reference to G. So I will have M A small UA and M A small UA T, and this is UAN. And G, I will also have I bar omega I bar into omega. So this is to differentiate this omega. This is not same as this omega. So I just put this with the superscript 0, right? Because you would have this is at the end of the deformation phase. So my angular momentum would be like this. So if this is so, now how do you apply your angular impulse and momentum equation? So you have to. So here it's very clear. This V is what is just before impact. U is what is the velocity, common velocity of the contact surface, but I consider only one vehicle, so velocity at the maximum deformation state. What is U? And omega is what is the angular velocity just before collision. Omega naught is what is the angular velocity at the maximum deformation point. So if this is so, now if I apply my angular impulse and momentum principle, what should I do? I should take moment about a convenient point, and the convenient point here is point G. So taking moment about G. So what will happen here? There is no moment by these two forces because that passes through the line of action of these two momentum are at G itself. So that won't participate. So I would have only I bar omega plus, and here you see I have this direction here like this, and the rotation is clockwise. So our convention here of the moment of momentum is counterclockwise positive, and here that is going to be minus r times integral p dt. So what is this? R is the perpendicular distance between this line of impact and this point G. So this would be equal to, here again, see these two forces are at G, so that won't participate here. Forces in the sense on the linear momentum are at G, so that won't come here. So I would have only I bar omega naught. So this is equation number 3. Then I can also have now linear impulse and momentum applied. So how do I do? So that I have now here at G MBA along n direction. So this M is mass of this body MA, right? Minus, because this force impulse is towards left, so that's going to be minus integral P dt, and that's going to be equal to here the linear momentum along the line of impact is MA UA M. So that's my equation number 4. So from equation 3 and 4, I can define now the Okay, before that, let us now consider the period of restitution and write the equation similarly, right? Now let's consider period of restitution. And in that, if I apply this equation, so what I will do, I will have an initial momentum at that time will be I bar omega naught minus R integral R dt. Because I don't draw now the diagram, the same impulse will be acting on it. See, this is for the same vehicle A only. I am not considering the other vehicle, only vehicle A. So this diagram here is drawn for a period of deformation. So during period of restitution, you would have this is replaced by integral R dt. And you would have this figure comes first plus R dt would be equal to this. So let me write the equation, you'll understand. So this is what is equal to here I bar omega dash. So omega dash is the angular velocity after the collision. So omega is angular velocity before collision of vehicle A as it execute general plane motion, and omega dash is the angular velocity after the collision. So this is the equation number 5. And similarly, if I consider the linear momentum, I would have now MA UA N minus integral R dt, that's equal to MA U VA dash. So subscript n is the component of VA dash along n, that's the meaning. So there is also a component perpendicular to n axis, and that is not to be participated in this equation. So when you are finding your final answer, you have to compose that velocities and you should write it. So this is equation number 6. So by having these equations now, we can find out E value. So from equation 3 and 5. Now I can write the definition for E. So how can I do that? See, find the impulses. So I have here equation 3. I have minus R PDT. So PDT is what is this? So definition of E is integral R dt to integral PDT, right? So now integral R dt, I want to get it from equation 3. So integral R dt, I will get it from equation 5. So what is that it's going to be? Let me take this as integral R dt. So if I have here R and here R, that goes off. So let me have this ratio is what is going to give me this. So if I do that, so I would have E value is given by, so this term goes on the other side, this comes in this side. So I have I bar taken out, and I will have omega naught minus omega dash by, am I right? Yeah, that's the equation. From equation 5, the numerator, and from equation 3, I'll get denominator for this. So again, this minus sign goes on this side, and this comes on this side. I will have I bar taken out. Here it is omega minus omega naught. So this goes off. So I have the ratio of omega naught minus omega dash by omega minus omega naught defines here coefficient of restitution. And if I multiply numerator and denominator by R, so if I take here R, because this definition, as per this, if I have to put here R, that's going to be R omega naught is what is nothing but linear velocity at the contact. So that's going to be R omega naught minus R omega dash by R omega minus R omega naught. So otherwise, what is R omega naught? Going to be UA of N minus R omega dash is UA dash of N by this is VA of N minus UA of N. UA of N. UA of N. So this is equation number. Let's call this is equation number 7A. 7A. So what is equation number 7B? So from equation 4 and 6, from equation 4 and 6, from equation 4 and 6, I can again get what is E, right? So that's going to be equation 6 by equation 4. If I do so, I get E as MAUAN minus MAEA dash N divided by from equation 4 I would get equation 4 I would get this right equation 4 I will have for a PDT, so that's going to be MA VA N minus MA UAN. So in this MA is common, that goes off. So I have UAN minus VA dash N by VAN minus UAN. So this is equation 7B. Now equation 7A and 7B refer to the same ratio, coefficient of restitution. So the numerator and denominator can be added together. So E would be UA minus VA dash N plus U. I have the same thing. What is the difference between these two equations? We have the same thing, right? We have the same thing. See the same thing here also. Whatever is the same equation, 7A and 7B, there is no difference, right? Is there any difference? There's no difference. So let me just look at again equation 4 and 6. AN minus UAN. Seven A and 7B. That proves to the same, right? So there's no need of rewriting this. Yeah, adding. And again, it is the same. See, I have the 7A and 7B is same here. 7A equals 7B. So this is now relating one body velocity after impact to that of the velocity before impact. Of course, there is common term here is the velocity of vehicle A during the maximum deformation. So similarly, I can consider consider vehicle B, and if you carry out the same, you would be able to get another set of equation for B. That would be appearing like that. That would be appearing like that. So that equation would be this. That equation will be this. So let me write. You'll have E value will be like you have this. You will have there VB dash N minus UB N by UB N minus VB N. And you would also have this equation. So now this has to be eliminated. So I can have this is equation 8. We can derive like this. Now equation 7 and equation 8 can be referring to the same. So I can take it like this. So E would be UA N minus VA dash N plus VB dash N minus UBN divided by PA N minus UAN plus UBN minus VB. So now you know what is this UAN equals UBN, because these two velocities UA and UB are different, but the component along the line of action, line of impact the same, So these two are equal. Hence, you would see that these two terms disappears in the numerator. Denominator, these two terms disappears, and you would end up with the equation required to define coefficient of restitution in terms of the relative velocities of the colliding elements along the line of impact before and after impact, right? So you have here VB dash N minus VA dash N by PA N minus VB N. So in numerator, what you have is relative velocity after a separation, after impact, relative velocity of two vehicles before impact along the line of impact. So this is what is going to be the required equation 2, what we have looked at. So now we'll improve. So this is how you can see the non-central collision, but yet we have the similar equation. What is the main difference there is angular momentum is conserved in this case, right? So how can you say that angular momentum is conserved is looking at non-centroidal rotation problems. So let us just now look at the same. If out of two vehicles now consider, both are arbitrary, they both are having some velocities as well as some angular velocities, and they collide. But if one or two are constrained, colliding bodies are constrained to rotate about the fixed point, in that case, it's similar to that of what? It's similar to that of a compound pendulum motion. The Charpy impact mission, you see that pendulum is hinged at one end and other end has got a striker, and it's a huge mass one which would be lifted, and then it is released. The potential energy stored is what is being consumed by breaking the specimen, where the energy absorbed by the specimen is called an impact energy absorbed by the specimen. And then you see after the impact, breaking the specimen, what is the potential energy, maximum potential energy of the hammer? The difference is what is used to calculate the impact energy of the specimen. So that we have seen. So you see that non-centroidal rotation are out of these two, one body is constrained like that. It is similar to that of compound pendulum problem. So let's look at again this body A, where it is constrained now at this point, hinged, say point O. If CG is somewhere here, and this is point A, contact point A, right? So this diagram would be it's what are these reactions. So free body diagram, if I draw, this hinge would be removed, and I would have there two impulse forces components. So this is qx dt integral. This is integral qy dt. And of course, I would have along the line of impact my deformation impulse P, deformation impulse P dt. So now, why did I take this now? Is because, so now this is equal to this. I would, I cannot say that. So this is, this sum is what is equal to, after. So you have, this is just at the beginning of deformation phase, and this is at the end of the deformation phase. So I would have again here the n axis. I will have here as it is p dt, and sorry, not p dt. P dt is taken here. So here, what will I have is I will have I naught omega dash, not I naught, yeah, I naught omega dash. And here it is, momentum is I omega, I naught omega. So I naught omega, I naught, not omega dash, omega power 0. Because it's a common velocity instant, right? So you will have like this. So I can apply now an angular impulse and momentum principle, I naught omega plus here. Since I take a moment about this reaction impulses won't participate. I will have this, and this distance now is what is at the distance, say r, then it is going to be r p dt. That's equal to I naught omega naught. Similar way, I can apply from this diagram for the same vehicle A, from this till the end of restitution period. So I would have I naught omega power naught minus r integral r dt. That's equal to I naught omega dash, I naught omega dash. So I can substitute from this for E integral P dt, sorry, R dt by integral P dt, and I can get my expression like this. QA n minus VA dash n by VA n by UA n as. So same way you can take the other body, and then you can get, and you will be able to prove the same. So it is same, one and the same, whatever we were doing it. The first one case what we have derived here is that arbitrarily they are not constrained. They have got an arbitrary motion. So both translation and rotation of its CG. That's general plane motion. So if that is so, you are applying this equation and able to prove your coefficient of restitution, And if the body is constrained, then how do you do is, it's once it is constrained, then there is no general plane motion, it is only rotation. The rotation is not at CG, it's about any arbitrary point in the body. So this point is constrained, hinged here, which is non-centroidal rotation. So this is non-centroidal rotation, specific case. So non-centroidal rotation, you see that you have only angular momenta and angular impulse, angular impulses, the impulse momentum, only you have in this, right? Okay, so if you have understood this, let us solve one simple problem and then try to comprehend our understanding. So, what is that problem is this way. So, I have one sphere. So, it's like a bullet sphere. So, the sphere is being sent with the velocity 5 meters per second. Just before it strikes the vertical bar rod, which is here placed, and at the top it is hinged. The top it is hinged, and this is free. So as this hits now, what would happen to this rod? So this is of mass m of r, that is 8 kgs. And the mass of the sphere is 2 kgs. Whereas the velocity of the sphere just before impact is 5 meters per second. And the velocity of rod is 0 because it's stationary. And the dimension of this is of length 1.2 meters, and it is a homogeneous bar. So its CG is located from here. And the distance 0.6 meters, right? So now what is the problem statement? As the sphere is being fired and as it hits this stationary bar where one end A is hinged, other end B is going to have a contact or impact from this sphere, from the sphere. And the sphere hits this at the velocity of 5 meters per second where this is stationary. So what would be the effect of this due to this impulse acting on it? It is going to rotate. This is going to oscillate. It's going to go angular motion. So it's going to rotate now about A. So there will be velocity after the collision for this angular velocity, and there is a linear velocity after the collision for the sphere. So you have to find B dash and B and omega dash and omega dash. So omega dash is what? Omega dash of R, because this only one element is rotating. This is translating element sphere. So it's simply omega R dash is what is its angular velocity. So that is what you have to solve. So how can you solve this problem? And you are given that during this impact, this is not embedding with that to have plastic deformation. Rather, it is semi-elastic deformation, and that is dictated by its coefficient of restitution value of 0.8. This is known. The characteristics of these two rigid bodies during collision would have coefficient of restitution 0.8. If that is so, you have to find out what is the velocity of the end of this rod, linear velocity, and its angular velocity. You also find out what is its velocity of the sphere after the collision. What is the velocity after the collision? So how do you do that? So how do you solve this problem? So you can imagine I have such a hammer here and which can oscillate. I can place here the vehicle and this hammer can come and hit this, and I can have what would be the side impact collision period. So like that I can assume. Or Like that I can consider, right? We have seen side impact problem by movable carrier barrier, right? So that would the barrier would be moving and hitting from the side of the vehicle. So imagine that this problem can be thought of this pendulum or this rod which can hinge can be given velocity of impact on that by lifting it and releasing it. So it will come and hit instead of spear here a vehicle from side. If that is so, there will be side impact problem. So we know vehicle stationary and it has been hit by that. So this mass or this effect, what is impinging on this can be an equivalent to another vehicle colliding. So like that, you can have an experimental setup for side impact problem. So if we have like that, you would be able to solve such problems. What would be the velocities after the collision at the contact point of this pendulum, as well as what is the velocity that is imparted onto the vehicle. Like that also you can do a reverse problem. So now for a time being, let's consider this bar is hit by the spear with the velocity and find out what is the velocity of the end of the rod, angular velocity of the rod and the velocity of spear after the collision. That's the problem. So how do you do? You have to apply impulse and momentum principle. So application of impulse and momentum principle would solve this problem. So how can we do that? So let's first draw the interest member, that's this bar. So this bar now this end is A, this end is B. I have to draw this uniform bar, not appearing like that, pardon for that. And this is your CG. So at CG, what is my momentum? So let me consider this spear and the rod as a collective system here. If I consider like that, I have here my linear momentum M R B R. That's before collision, and this is going to be M I bar into omega naught, I bar into omega naught. And the spear here, uh, just a minute. Just a minute, I just request the teacher, other teacher is speaking from the cabinet. Okay, thank you. See, let's finish it in another 5 minutes also. Please be patient. So, here I have the system of bodies. One is the spear, another one is the. So, at the time of contact, I will have here its linear momentum is MSVS. And I have for this. So, since it is stationary at the beginning said, this is going to be 0, VR is 0, and this is also going to be 0. So this now plus the total impulse that is acting on this. So what is that impulse diagram I will have? At this contact, the maximum deformation, end of maximum deformation or the end of deformation period, I will have here the impulse that is AX dt, AX dt, integral AY dt, AY dt. And here there is an exchange of that gets cancelled. That's why it is not that stationary when it hits. So you exert the force and the same would be exerted. I don't draw here this. Instead, I put only at the reaction impulses here as an external. And that's going to be equal to the momentum after the hit. So it's just going to separated from that. So the velocity of this would be now in what direction? We do not know, so let's consider as it's going hitting and then it goes further like that instead of bouncing back. Let's consider according to the direction of and the value you would be able to make out. So this is MS into VS dash after collision. And I would have here, this is going to have definitely now some linear velocity. That's going to be m r v r dash and I g p omega dash, I g omega dash. So that is all. Now here I can apply linear impulse and momentum and solve for this type of problem. So how do I do so? So if I apply now angular impulse and momentum here, taking moment at point A, then I will not have these impulses present. So I will have initial momenta before collision would be equal to momenta after collision. Because system external impulse is going to be momenta due to that will be 0. So I would have here now ms ds and its moment about this point A. So this height is the length is 1.2 meters into 1.2 plus this is all going to be 0 as here I will have the exchange of this. So momenta due to this and this will be cancelling. That's why this is 0. And in this side, I will have ms vs dash into 1.2 meters. And here, when I write this, I also have to write these two. This I'm writing it for sphere. And here it is 0. Since these are 0, I don't have these terms. Whereas here I have all these three terms. So plus Ig omega dash plus mr pr dash into 0.6 because this length from here is 0.6. So this is the equation number 1. So by substituting the values here, ms value is 2 kgs, vs is 5 into 1.2. That's equal to 2 into vs dash is unknown into 1.2 plus what is Ig here? Ig, by the way, is uniform rod, so it is the ml squared by 12. We can prove this, and this is the formula. So mr here. So that's going to be 8 into 1.2 squared by 12. So this value is going to be something 0.96, 0.96 kg meter square. So I will substitute simply that to 0.96 to omega dash plus VR dash. So VR dash, I can rewrite that as how it is VR. So it's going to rotate about this, constraint to rotate. So if this is rotating, the linear velocity at this point would be VR dash is R times omega, this distance times omega. So I'm writing that as 0.6. So the mass of this is 8 kg into 0.6. This is 0.6 times omega dash. So 0.6 times omega dash into 0.6 here. And I would have here this equation reduces to 12 on this side. This side is 2.4 Vs dash plus 3.84 omega dash. So this is equation number 2. So I have now one equation relating what is my interest. Vs dash and omega dash, omega r dash. So once I have this, I can find out, of course, this 0.6 times this. So that's not an issue. So, but only one equation I have. So what is my second equation? My second equation is from coefficient of restitution. So coefficient of restitution is defined how it is dv dash relative velocity after the collision, dv dash minus bs dash equals E into Vs minus Vb. So that's going to be Vb dash is what is 1.2 omega dash minus Vs dash is to be found out. That's what is equal to 0.8 times Vs is 5 meters per second minus Vb at that time is stationary 0. So I will have here the equation as this. So minus Vs plus 1.2 omega dash That's equal to 4. That's equal to 4. That's equation number 3. So now I have equation 2 and 3 can be simultaneously solved. I'm solving that. What do I get? I'll get the velocities after the collision. So Vs dash would be Vs dash equal to 0.143 meter per second. I get that's minus value. So it's clear that it is reversing. So that's going to be 0.143 meter per second this direction. And what is omega dash? By solving this, I get omega dash as 3.2143 radians per second counterclockwise. So the rod is rotating this direct angular velocity. If that is so, I can find what is VR dash. So or VB dash. So VB dash is 1.2 times 3.2143. That's going to be how much it is? 3.86, 3.86, 96. This direction. So one can find out all this. So finding this, what is the advantages that we can calculate? What is the energy loss? So energy loss now is given by initial kinetic energy minus final kinetic energy after impact. So initial kinetic energy is what? Initially, the system kinetic energy is half into 5. Mass of the ball is 2 into speed is 5 square. Only kinetic energy. The bar is stationary, so there is no component of energy. So the system initial kinetic energy at the beginning of impact is only this minus final kinetic energy is you have both elements. So half into ms, that's 2 into Vs dash. Vs dash we calculated here 0.143 square. And other energy is the bar kinetic energy. So bar kinetic energy can be expressed through half into I naught into omega dash square. So where I naught is bar moment of inertia about the top point, IA you can put. So if I do that also, what is that I have? Is this 25 here minus 19.86. I have 5.14 Newton meter is the energy loss. And I can calculate what is the percentage energy loss simply by initial kinetic energy minus final kinetic energy by initial kinetic energy. So it's lost by KE1. That's going to be 5.14 by 25. It's 0.2056. So it's going to be 20.56%. So the amount of energy that's lost because of this collision, which is non-centroidal collision, is this much. Right? So this is how you can look at a simple problem. But the fundamental principle, how can you apply is what you have understood from today's class. And we will look at now in detail how it can be further seen as described in the textbook in the next class. That's tomorrow morning, 7:30 to 9. We'll have 2 periods. And then let me also plan tomorrow. You have D2 slot, afternoon free. I will take 1 lecture possibly. And then Friday morning 1 lecture, 10 o'clock. So that we would be able to compensate some of the missed classes. So with that note, let me stop for now this point of time. The lecture if you do not have any doubts.